Okay, so the point of this video is going to be that I recently read this paper that you can see on my screen. Not virtually, I got a printout of it and then read it because it's bad to read on my phone. And so the point is that I in this video will try to make myself clear about what did I understand in this paper, because for one thing, this paper was good. Since see, I have liked reading for many years now, and I'm reading papers, not papers. This was the first and the only paper that I have read as of June 2020, July 2022, 2026, and I aim to read more papers because this was fun, and if this was fun, others will also be fun, I believe. It's raining outside. I think you cannot hear it, obviously. So the point is that I will now try to explain a paper that I read 2 days ago, and it's because I watched a video about Benjamin Franklin, that how he read something and that then again after a few days, firstly he read something, then he absorbed it for like a couple days, and after that he would try to write down and explain the content that he read, and since he won't remember it word by word, he will have to explain it in a way that he himself understands it, because if he don't understand maybe a part of it, he would not be able to explain it. I have the physical paper with me, and I have highlighted a few points that I really want to share because they were fun, and I like this paper also because it did not have much math, and honestly I don't really hate maths, but see, I just passed 12th grade. Okay, honestly, one thing as well, I don't care how long this video is because I'm just here to blabber, right? So the thing is, I just passed 12th, and whenever I see the thing holding me back from reading the paper of who was that guy, Dyson Freeman, the 2 papers that he published, which we will be talking about in this paper. He published those 2 papers, and I saw those 2 papers, and it freaked me out because it was a hell lot of math and I could not understand it. See, one thing I want to make it clear, that if you look at me and see that I'm reading a paper, don't assume that I am a highly intellectual guy, because as much as we read about quantum mechanics and things like that in up till 12th grade, I know only that much, and plus what I read in this paper, just this much. I don't really have an understanding of quantum electrodynamics and quantum field theory and special and general relativity. I just have heard that. I actually tried reading about the special and general relativity in December. Yes, not December, but even before that I tried reading about it, and I just could not like the first few pages itself, about talking about frame of references and coordinate systems moving and not moving. I believe I would have understood it if it were explained a bit better, but I cannot blame the guy for writing it. It just might be my fault, but I will eventually understand, because at the end of the day, what I believe it that they just were interesting. Okay, so what I was saying was, I like this paper because even though it does contain some maths, like on this page, on this page wait on this page, where you see the topic of understanding Feynman diagrams, no, doing physics with Feynman diagrams. In this page we have we have some math, we have some integration, and that much is obviously okay with me, because this guy explained what each and everything meant, and that's why it's fun, right? So it contains maths, but only that much that this guy has explained as well. Yeah, and it has photos as well. Just look at this photo. I mean, what do you feel when you look at it? Yeah, do you feel something when you look at this photo? It's a photo of Richard Feynman with a few other theoretical physics people. I don't know how do I explain this, but it just feels a bit, not a bit, it just feels highly interesting to look at a photo like this. Like, they just huddled up in a space and thinking about quantum electrodynamics. How cool is that? I don't really know people around him. I just read the names because the names are written there. This is, by the way, June 1947. This is the year that India got its independence. So yeah, and below that also there's a diagram of a Feynman diagram, which was one of the first and made himself by Mr. Richard Feynman. And yeah, okay, this was the introduction, I believe, and now we will start with actually the explanation. Okay, before that I will show you my setup. So whenever there is something that needs to be taught or explained by writing, I will not write it here, because this is a phone and I cannot write it with my finger. I don't have a stylus, so I have this setup. There's a giraffe and a zebra sitting here, because even if this video gets no views, they are the two viewers and listeners and my audience here. So don't feel bad if I don't look at you. I will be looking at them for sure. This is the board and this is the table, and this is the setup. The numbers written there were actually written yesterday when I was trying to make students understand how to arrange 3-digit numbers in ascending and descending order. Yeah, so I will just rub them off if needed. Okay, so let's actually start with the paper, and the paper's name is Physics and Feynman Diagrams, and the subheading says that in the hands of a post-war generation, a tool intended to lead quantum electrodynamics, which they say as QED in the paper and usually as well. Quantum electrodynamics out of a decades long morass. Okay, morass is a word which means a situation difficult to escape. A decades long morass helped transform physics. Okay, it's a pretty good headline. It's like the teaser of this paper. This paragraph is about David Kaiser and what he was a part of and what he does currently, and I believe this guy was cool because this paper is cool and he wrote this paper, right? Okay. In the first paragraph, we are told about a person named George Gamow, who was a theoretical physicist who studied and talked about Big Bang and that whole niche of physics. And the paper says that he was like a master at it at his work, and it also says that he could lie down on the couch and close his eyes and no one would ever know if he was working or not. I don't really understand what is the point he's trying to make here. It can mean two things. It can mean that for me it can mean that theoretical physics is such a work of the brain that sometimes a master can do it in his mind and he does not need paper, and it's not like other work where you physically have to be present and move your hands and legs and speak and do something. It might be this, or maybe it just says that George Gamow was a chill guy. Yeah, it says that he was a fine gag but a bad model for thinking about day-to-day work that theoretical physicists do. This the few initial paragraphs also talk about how there's a difference between labor, activity, skill and physical things from the conceptual and theoretical ideas. Yeah. Okay, this paragraph, see, I already told you that I will try to explain what I did actually understand and I will not explain what I did not, because I am not a theoretical physicist. I have not even gone to college yet. So this paragraph, this paragraph I am highlighting as a whole, and it's not because it's something I like, because it's because I did not understand 99% of this paragraph. So I'll just read it out. In the accounts that resulted from such studies, the skilled manipulation of tools played little role. So it's like they're saying that that manipulation of tools, that actually just knowing how tools work does not really account much to what he's talking about. And then he says about that ideas travel from theorist to theorist, and then this thing in the brackets, in the parenthesis, tied as they were to the electron microscopes, accelerators or bubble chambers. What was that a joke? Actually, I did not understand. Ideas embodied in texts traveled easily from theorist to theorist, shorn of the material constraints that encumbered experimental physicists. Okay, wait. It is saying that every idea that okay, it says that every idea that traveled from one theorist to other, shone off means it smelled of, or it kind of gave an idea about the material pleasures of that theorist from which the idea is coming. So like, if a physicist or theorist has microscopes or is usually in close vicinity of accelerators or bubble chambers, his views will smell of that material equipments or things. This is what it says, and I might not be correct as well, but okay. Okay, now in the next paragraph, he was like defending theoretical physicists, saying that they have not spent their, oh my god, they have not spent their days and nor their nights, because nor their nights in the dream world of concepts and dreamy theories and things like that. They have put their work into calculations, because yeah, calculate, oh ho, calculate. And he's trying to say that how theorists calculate the absurd calculations and observations, and then actually provide a framework for further physical observations. So he's basically saying that theoretical physicists are not bad people. Yeah. Then he's telling about what he has done in this paper is taken the view of a tool, and he's talked about Feynman diagrams. So this tool was something that, see, Feynman diagrams, I for now know that were a tool to initially solve problems in quantum electrodynamics, which had two major problems, which is on the next page. And this tool was like, it just was a supplement to a huge chunk of calculation. So either you can just go on and on calculating a huge chunk of like algebra of which extended to 4 or 5 lines as quoted in this paper, or you can just make the diagram and get away with the calculation part as well. Like, of course you must know what is going on in the math, but the diagrams in some way helped you with easing off the calculations, and that's how it revolutionized nearly every aspect of theoretical physics. And this is because at the end we get to know that Feynman diagrams did not remain constrained only to quantum electrodynamics, but also spread out in nuclear physics, nuclear reactions, solid state physics, if I am not wrong. Yes, solid state physics was indeed a mention. Yeah. And so it spread out and people started using them not just for quantum electrodynamics, but however they wanted to use, and in whichever field of physics they wanted Feynman diagrams to be used, and that is why it's written that every aspect of theoretical physics. Yeah, but of course it's also written that tools does not work for themselves, and then if there was a tool that was made, people need to understand how to use them, and then people they understand how to use them and then use it. Okay, so the aim of the paper is actually, according to me, this paragraph, this which oh no yeah this paragraph. My research has therefore focused on the work that was required to make Feynman diagrams the tool of choice. This paper is aimed to make you understand why Feynman diagrams was a tool of choice. Okay. The word that keeps arriving again and again is that Feynman diagrams are a bookkeeping device. They are a tool that you pull out every time you need them. Yeah, this is a word that occurs very frequently. They were introduced in the 1940s, and see, this is what is written. Not long thereafter, other theorists adopted and subtly adapted to Feynman diagrams for solving many body problems in solid state theory, right? And then some people went on with Feynman diagrams in gravitational physics, and this was something that I really like about Feynman diagrams, is that people have said that with Feynman diagrams we were able to calculate things that many had barely dreamed possible, and we have an example in this paper as well. I guess it's where in the last second page, I think. Yes. Who was that guy? KROLL, I think, who said it. We'll see further. Okay. It might be said that physics can progress no faster than physicists' ability to calculate, and this paragraph tells you that how and why Feynman diagrams were useful, because they just sped up calculation, so you can do more physics in less time, right? Okay. Stuck in the mud. Stuck in the mud. Stuck in the mud is the name of this paragraph, because it's going to talk about what problems there were, the two problems that I told you about. It's going to talk about that two problems before the introduction of Feynman diagrams in quantum electrodynamics. So this paper has so many photos as well. There was a meeting in where was it, Pocono Manor in rural Pennsylvania, and in that meeting only Richard Feynman first introduced his method of Feynman diagrams to other 28 theorists. Okay. We'll look at this photo as well. This is not Richard Feynman. This guy is this Mr. is not Richard Feynman. He is David Gross. And who was he? David Gross David Gross was himself a Nobel Prize winner in I don't know what, but yeah, there's also a term QCD, and QCD means quantum chromodynamics, and I don't know what chromo actually means here, but we'll just continue. I will look. Yes, I must highlight what does chromo mean actually, and if you want to know also, you should go and check out what this chromo means in quantum chromodynamics. Dynamics means movement, quantum means on a very small scale, chromo means color. Chromo means color, right? Chromo means color. Yeah, this could be the word. Okay, but I'll check. So they're basically talking about and discussing about quantum electrodynamics problems only on this blackboard, and they are indeed using Richard Feynman's Feynman diagrams here. Okay. I actually don't read photos in between reading paragraphs. I first finish a paragraph and then read it. Okay. So it says that most physicists at that time in 1948, around that time, physicists were deeply thinking about and trying to solve questions in quantum electrodynamics, but also these problems were non-trivial, and that means special, right? That means that they were special problems. And this paragraph is again a good one because it tells you what quantum electrodynamics roughly is. Yeah. Quantum electrodynamics explains the force of electromagnetism, the physical force that causes like charges to repel each other and opposite charges to attract at the quantum mechanical level. This is what the definition or a rough understanding of quantum electrodynamics is. It tells you the reason of attraction of an electron and a proton and the repulsion of two electrons or two protons, right? Let's just, sorry for the voice. Okay. Yeah, this is something that I highlighted in my physical copy, from this into this force, and it's because it tells you that in quantum electrodynamics the electrons, what they do is the electrons and other fundamental particles, they exchange virtual photons. Virtual photons are not real photons. They do not exist forever, or like it's like they come into existence for a short period of time and then they vanish again. So if you want a backdrop of this thing, it's like it's a virtual particle, they say, is like a ghost like particle, and it's a carrier of force. So See, a virtual particle is one that has borrowed energy from the vacuum, briefly shimmering into existence literally from nothing. Virtual particles must pay back the borrowed energy quickly, popping out of existence again on a time scale set by Werner Heisenberg's uncertainty principle. See, virtual particles like the photon that electrons exchange come into existence. They borrow some energy from the vacuum itself, so they are literally being born out of nothing, and they get born, they get exchanged, whatever they do the thing, and then they go away again. Now this was highlighted also because I did not expect the paper to say popping out of popping out of existence, because I had also read a book named A Brief History of Time by Stephen Hawking, and in that also he also talked about virtual particles and particles which come into existence just like that. And what he told in that book, if I remember correctly, see, I'm just making assumptions and remembering things out of memory. Please don't by heart what I say as a true fact, okay? Because it's what I know and what I think is true. So from my memory I remember that when I read that book, even though I did not understand a major part of that book, in when he was explaining about virtual particles, he said that virtual particles come into existence with their opposite particle. Like if like it's no, it's the antimatter thing, or what is that, anti-neutrino. See, if a particle is coming into existence, it comes into existence with by pair, the particle and its counter, neutron and anti-neutrino, something like that. I am mixing up terms, I know. Neutron and anti-neutrino are not opposite particles, but something like that. And so it was not like it comes and goes, it's like the positive energy comes into existence with the negative no, not energy, like a positive charge comes into existence with a negative charge, so that overall the net effect is still cancelled out and no energy has been actually borrowed. So if one particle is borrowing energy, the other is giving energy to come into existence, and so the net exchange is remaining zero, and so it does not need to again go out of existence, popping out of existence again. But okay, if this paper says that virtual particles move out of existence, then I will take it for now as my homework to study about them as well. Okay, done. Question mark made. And Asha, by the way, I was I read this paper 2 days ago, and today morning I was reading the chapter States of Matter, which was skipped in class 11th chemistry, physical chemistry. I was just reading it for fun, and in that I discovered a page which said that it was talking about dipoles, and yeah, this one is something I need to discuss. Okay, so if I just do this and maybe do this as well. Yes, perfect. So let me just open that page because it's my choice. I will stop the discussion of this paper for now and I will open that page. And yes, this was the page. If you can see the highlighted thing, let me just, yeah, now you can read it. It says that partial charges are always less than the unit electronic charge, and I have studied about partial charges many times in 11th and 12th. Any 11th and 12th grader from PCM or PCB must might be knowing about partial charges. That is basically the delta thing, you know. Okay, if you don't know what I'm talking about, just give me a minute. I'm talking about this thing. So if there's a bond between H and F, hydrogen and fluorine, what happens is, because fluorine is so electronegative, it pulls the electron cloud or electron density towards itself. Even though I have heard the word electron cloud maybe like 1,000 times, I still don't understand, by the way, that how electron can be a cloud. Does that make sense to you, that electron can be a cloud? I must also read about this thing as well. Okay, so for now we'll use the word electron cloud because teachers in my class have used them. And okay, so it pulls away the electron cloud towards itself because fluorine is a more electronegative atom, and because of that there's a small delta negative charge on fluorine and a small delta positive charge on hydrogen that is induced. Okay, now the question that came into my mind because of this highlighted paragraph was that how can charge less than and the charge of an electron exist, because does this not in a way contradict charge quantization? This was the question. If there's a charge induced here and this charge is less than, so we'd say that okay, not here, we say that this delta negative on fluorine is less than the charge of an electron. How is this charge then even existing in reality? Don't you think that a charge less than an electron cannot exist because of quantization? I think I'm missing something. I must read something about it, but it's just a curious question. If you know the answer and you want to reveal the big thing, you can in the comment section. It's your choice. So this was a question that came into my mind when I was reading this, and because this yeah, one more thing. The thing is, I can just Google or ask an AI why is this the case and it will give me an answer, but I choose not to. I choose not to because I believe that that will be just like killing the intellectual something inside me. I do usually ask AI, but this thing, I believe I don't have any deadline or an exam coming up right now, so I can just live with this question for at least a week. And what I have thought about is, I will think and then try to write down an answer. Even though that answer will be completely useless, it might be not even close to the actual answer, I will try to write an answer and Then what I'll do is I will ask, so that it's just more fun that way. I don't really know if I justified why I'm doing this, but it just feels a bit more better. Okay, now I believe we can continue with the paper. Also, it's approximately 4 o'clock, so the students are coming actually. So I will just stop this video for now, in a few minutes, and then continue it with the second page that we were reading. But for now, let's just read one more paragraph. I think one more paragraph is not going to, because they have not arrived yet actually. Okay, so this one. Okay, this one. Yeah, now this is where we talk about the two terrific problems marred physicists' efforts to make quantum electrodynamics calculations. First, they had known since early 1930s quantum electrodynamics produced unphysical infinities. So the first problem was that whenever people or whenever physicists were trying to do calculations on quantum electrodynamics, because a photon can come into existence, it can borrow some energy, and there is actually no limit to what energy it can borrow, and so it can even borrow an infinite amount of energy because it will return it in some time. So it can even borrow infinite amount of energy, and because of this thing, what happened was the calculations in quantum electrodynamics was producing unphysical infinities rather than a finite answer. That was the first problem, and that happened when it was pushed beyond its simplest limits. So if you are talking something simple about an electron or the interaction, it will not produce an infinity, but as soon as you push its limits, you ask questions that something like, it's written that for instance, what is the probability that two electrons will scatter? If they ask a question like that, theorists will eventually get a rough and steady approximated answer, but as soon as they tried refining about it, like they have not actually given a question that could not be answered, but I believe if they can get the answer of the probability of two electrons being scattered, let's say a question was, when will it scatter, or what at what position and or what momentum does the electron has when it scatters. If they ask questions like this, I believe that was the breaking point of the equations in quantum electrodynamics, and that was where unphysical infinities were being produced. See, this is what highlighted here. We have moved on here. It says that the problem was that the force carrying virtual photons could borrow any amount of energy whatsoever, even infinite energy. That's what I was talking about, as long as they paid it back quickly enough. And infinities began cropping up throughout the theorists' equation, and their calculations kept returning infinity as an answer, rather than a finite quantity needed to answer the question in hand. That was the problem. That was the first problem. That was the paragraph that talked about the first problem. Now the second problem was that formalism in quantum electrodynamics was notoriously cumbersome. It means that the algebraic calculations and the hard and steady observation and then calculating long, it was a bit too much to do. It says that an algebraic nightmare of distinct terms to track and evaluate. In principle, electrons could interact with each other by shooting any number of virtual photons back and forth. See, in the simplest case, the electrons only exchange one photon, but in reality, they can exchange any number of photons. That was the problem. The more the number of exchanged photons, the more cumbersome and the more difficult the equations and the calculations became. The more photons in the fray, the more complicated the corresponding equations. And yet quantum mechanical calculations depending, see, it says that the more the number of photons, the more cumbersome the equations become. But even still you cannot ignore those photons. Each and every photon need to be tracked down to add up into the contribution overall. You cannot miss them because there are so many, because then you'll just have the wrong answer or the not so perfect answer, right? But then it says all hope was not lost, and then it talks about a few very familiar names like Heisenberg, Wolfgang Pauli, and Paul Dirac. And yeah, we'll just read this paragraph and then we'll study continuously. I will just make a cut here. 158. So it says that all three of these people and the other interwar architects of quantum electrodynamics knew that they could actually approximate this calculation, and it was because of the fact that in those calculations they had the multiplication of the charge of an electron, and we know that the charge not that just E, the charge of single electron, they had the multiplication of E square and E to the power 4 and sometimes E to the power 6, and that would significantly reduce the number down. And see, it's written that by the way, this photo, Richard Feynman in the middle along with other great people. So it says that every time a pair of electrons traded another photon back and forth, the equations describing the exchange picked up another factor of this small number E squared. So whenever a single photon was exchanged, the equations governing would pick up E square, and multiplying by E square is a very small number. The approximation is 1 over 137, and the actual value of E is, as we know of now, is 1.6 into 10 to the power minus 19 coulomb. So that too squared is insanely small than 1, and so it will reduce the number. Picked up another factor of E square. So a scenario in which the electrons traded only one photon would weigh in with the factor of E square, whereas electron trading two photons would carry the much smaller factor. So if two electrons traded or exchanged two photons, the number would go down even more, because it will be then being multiplied by e raised to the power 4, e square into e square, that is e raised to the power 4. Then for 3 photons it will be e to the power 6. And it says that they were the physicists at those time, those he named as Wolfgang Pauli Heisenberg and Paul Dirac and other interwar architects. They believed that they could solve these problems. Was that because if you increase the number of photons, the magnitude of the power on E, the charge of an electron, would increase, and like if 3 photons are traded, the power goes to e raised to the power 6, which is then again very small. So after a certain time, after a certain number of photons, you don't need to calculate for other photons as well, because the contribution that they will make in the calculation will be in 0.0000 so on till a very later digit, which could be in principle ignored to be efficiently doing the calculations. It says that although the full calculations extended in principle to include an infinite number of separate contributions, like if electrons can indeed exchange infinite number of photons, then in principle we should consider the contribution of infinite photons, but that would just be not so useful because of the thing that I explained, that they will contribute to a very later digit in the number that you're trying to arrive at, right? So it's like, if I give you the analogy, if it's like after the fifth electron, the fifth photon exchange, the sixth photon exchange would contribute to the answer as it will add 0.00 till the 40th decimal place, 40th place after decimal, and it will change that place by a factor of 3. Then you can just ignore it. That is what it's this paper is trying to tell, that kind of contribution can be ignored. That's what I think I have understood here. Okay, let's just stop for a second here, because I believe I must listen to the call of the duty here. By the way, it's going to be an hour of me blathering, and there just might be a chance that someone on YouTube is listening to me right now. So before I go down, what do I say to you? Thank you. I believe thank you for staying and listening. And if you are listening, this means that what I am saying is interesting. So thank you for that. And if you're not listening, if there's 0% here, I don't give a